Hey guys,
Hi.
we are at the end of November.
Happy Thanksgiving.
The 28th of November, guys, it's almost Christmas.
That's
Holy
crazy.
cow. I haven't done any
Are you
Christmas
ready?
shopping. We do have our tree up at Harmony,
Yes.
and it's got a Harmony topper instead of a star, of course.
The Harmony is our star.
Yeah, well, you know, we're a little bit weird like that, so it's okay.
All right. It's good.
So we have a number of things to talk about. We better jump in before we make this a 45-minute video.
Right, let's not do
Because
that.
you are full of hot air. And I'm sorry, did I say that out loud? So anyway, Bucknell.
All right. Let's talk about Bucknell. They brought our turbine back.
Yeah.
They are done.
They're done with their testing. Their project is concluded. So I'm here with Professor Nate Siegel from Bucknell University. He came down today to deliver our little baby back to us. So what are your thoughts about the project?
The thing with the Savonius turbines, if you look in the literature, you can see a bunch of people have done what I'm going to call combinatorial studies or parametric studies, where they vary all of the primary geometric parameters, and they show turbine performance that's all over the map.
Right.
All the way from some up near 27%, 28%, all the way down to like 1.5%. And the shape of the turbines could maybe only be subtly different, and you see this massive change in performance. Right. And so the geometry is important. There are other attributes, I think, that could be added relatively easily to improve performance. Like one of the things is the aspect ratio of individual stages. So when you look at most of the high performing Savonius turbines, they are single stage rotors that have a relatively large height to diameter. That's the aspect ratio.
Right.
And in the multi-stage versions, they show that there's a deficit in having too low of an aspect ratio on each stage. But if you were to stretch out the stages, you can actually start to see less and less of an effect on aspect ratio until you get to some point where it doesn't matter anymore.
Right. So one of the things that we were talking about with Dr. Siegel, Nate Siegel, was aspect ratio. And we were talking about the height to width, or the aspect ratio, and that refers to the individual scoops. So in this design, we have about a 2-to-1. We have 2 times the width to 1 times height there. It's just like when you're baking, and it's a 3-to-1 ratio of flour to sugar, whatever. Here we are 2-to-1, 2 in the width to 1 in the height. And here we have something that is more of a 1-to-1, 1 width to that same height. So the scoop geometry and that height to width relationship is important when we're doing our testing. Here we have one that is like a 0.5-to-1, so, or even a 0.8-to-1. It's much, much taller than it is wider. So we're looking at those scoop geometries, and that relationship, the aspect ratio relationship, is important in some of the research that we've been doing.
Aspect ratio, spacers in between the stages to prevent basically tip losses, where the air is coming in and just sort of short circuiting and going around the outsides. I think these are easy mods to the design.
Yeah.
That would get you 5-10 percentage points. The other thing that I mentioned when we talked last and in the reports was the fact that the tip speed ratio is down lower than where we would expect it to be for peak performance. Typically, you'd expect it to be at 0.8 or 1. And the test data that I got, it was considerably lower than that, which I take to mean that we're not getting as much of the lift component
right
on the torque as part of the overall torque summation as we would expect to get in a really optimized geometry. And that could just basically be tweaking the airfoil shape a little bit, right, to get that boost. And there are lots of examples of turbines out there, including the one from Modi's paper that has geometry that does achieve that.
Yeah, and his geometry had something like a Q to an R or whatever.
It was a little bit different. So I tried to point out where the differences were in the shape of the airfoil.
Right.
And I think it might actually make a pretty big difference at your 25 mile per hour design point.
Right.
So,
yeah, I'm really curious to see once we finally start getting some data from our own generator, literally putting it right on the bottom of the unit and then driving that unit in natural wind conditions to start.
Yeah, we were
doing
pretty
our best.
happy with towing the turbine around
Mhm.
in the U-Haul, and we found that you really don't need much more than a mile to get a data set where you've got relatively consistent rotation, relatively consistent wind speed
Yep.
for a long enough period of time that you get a pretty good data set.
Okay.
So we would just go back and forth over this 1 mile course where it was relatively flat. There were no turns or
Yep.
dips or anything.
I guess so. Bottom line, the data you were seeing was fairly consistent with your wind tunnel testing.
Uh-huh.
And, what would a takeaway or a soundbite, whatever you want to call it, if you could sum it up? Or
Well, what I would do, so I would say that the system needs only a few geometric changes to get performance consistent with what I would consider to be the best examples of Savonius turbines.
Okay.
I think that one of the I think most valuable takeaways from the work was that the wind tunnel testing appears to be useful in predicting or at least showing which geometries are relatively better than others.
Yep.
So that's a really nice thing because you can test at small scale. And we didn't even totally match Reynolds numbers and everything. We got close for some of the range, but we weren't complete. We didn't have complete what we call dynamic similarity. Mm-hmm. But still, we were able to show the results matched pretty well.
Okay.
And so
there was a strong correlation.
Anything that is good on the wind tunnel is probably going to be good at the full scale.
Okay.
So as far as testing out geometries that maybe your simulations have shown are going to be good, I think the wind tunnel is a pretty good way to go.
Okay. Well, overall, I'm happy with how things turned out. It's one thing to hand your baby to a university and say, here, guys, test it. But, to come out with at least mostly favorable results and the findings are at least predictable along what you were looking at, to the point where a few slight changes should give us marked improvement in our performance.
That's what I'm expecting.
Well, that's really cool.
All right. Thanks.
Well, thank you, Nate.
Thank you.
When Nate came down, the professor who was leading the project, he said, there's some things we would have done differently had we known now what we didn't know then, or however that saying goes. But they learned a few things along the way. And one of them was that the prony brake they were doing, it was a resistance brake that they were trying to squeeze onto either bicycle or motorcycle brake pads. It was a little bit complicated. They had to calibrate a lot of things. They had to try and get a number of things all working together. And in the end, he said, you know what? We started doing research on eddy current brakes, and had we just done that, it would have been so much more simple. So Nate and I were talking, our Nate, we were talking with Nate Siegel from Bucknell and saying, well, tell us a little bit more about this easy way. And he explained a little bit about the eddy current brake, shared a little bit of literature with us. We looked up a few things on our own, and lo and behold, it was drop dead simple, guys. So for 2.5, 3 years, we've been saying we need data, but we have never had a good way to get data and also make that thing, whatever it is that we come up with, mobile, so we can take it on the road, because we all know Pennsylvania has sucky wind. Well, the eddy current brake is the answer to all those prayers. So we're going to show footage of our eddy current brake and let that explain it for us. So it's this crazy contraption that we've built.
Yeah, so you can see we have our full turbine here. And one of the things that we needed to do was to be able to test how it performs. So we came up with a pretty cheap way of measuring. So we wanted to be able to measure the torque and also the RPM, so that we can then calculate the horsepower, which gets converted into wattage. So why don't you explain how the eddy currents actually work?
So when you have any non-ferrous material, such as copper or aluminum, it's not magnetic, so a magnet won't stick to it. But if you take a tube of copper or a tube of aluminum and drop a strong magnet through it, try it sometime, guys. It's actually like watching an astronaut tumble in space as that magnet goes down through and falls very, very slowly through that tube. That's because of the eddy currents that strong magnet is inducing in that tube as it falls. That same action applies here, where you have a rotating disc and then magnets underneath it. As the disc rotates, you'll see we're at 0 right now. And as we start rotating, we begin to get a pull. So these magnets are trying to be dragged along with that disc. Even though it's non-magnetic, the aluminum is trying to drag those magnets along with them. And we simply measure, what is this guy called, a load cell?
Yeah, we got a load cell. It's an S-beam load cell. I think it goes up to 700 pounds, so it's a little higher than what we need.
Way higher than what we need.
But so that will measure the torque, so we know how far these where we're attaching to the magnet plate. So we know that distance, and then we just multiply it by the load, and that gives us the foot-pounds.
Yep. And once we have the foot-pounds and the RPMs, then we can calculate the magic thing we've been after for years, which is our wattage.
So we also have like a tachometer where, it's connected to my phone, actually recording data now. So if Chris spins that, you can see we can just be sitting in the back of the truck or somewhere reading the RPM live. So that's kind of what we're getting. It's recording it now. And then we'll be recording the load as well. Come back and we'll know how fast we're going, and we'll be able to start figuring out the performance of this guy.
The cool thing is we don't need to calibrate all these very difficult things with this design. All we need to do is have a calibrated load cell, because whether we had these magnets out 2 feet or 1 foot or 6 inches like they are now, we just simply take that known distance and then multiply that by the force that's pulling. And we have a very simple way to then calculate that foot-pounds. Where if you use a prony brake or a resistance brake or a friction brake, you've got to calculate all kinds of things. You can't just do it as simply as this eddy current brake allows us to measure one thing at the cell itself, how hard it's being pulled, how hard as we pull on this, how many foot-pounds we're getting. So we calculate our distance times our foot-pounds and then factor in the RPMs, and we get our wattage.
Yep.
Which is huge, because 3 years I've been saying we need wattage, we need data, and the wattage is how we get that data. So this gives us exactly what we're finally after. So one thing's for sure, we need heavier coats before we do field testing in the winter.
It's cold, but it's windy.
Yeah, so guys, what you're looking at here is our eddy current brake, and it is functioning. We're picking up our foot-pounds of torque. So and this little guy in here is the magic piece. This eddy current brake allows us to actually get data in real time of how many watts we're producing, because we take our foot-pounds of torque times our RPMs, and we can come up with an actual output.
Yeah, so we get the horsepower, which we can convert to watts. So we'll know at a given wind speed what our wattage will be when we produce it.
Yeah, so it's really actually quite amazing how simple it is. And I'm freezing to death, so I think we'll combine this with the inside footage. So basically, that eddy current brake that you just saw is a very simple way to get data. Bucknell did something similar. They did a prony brake with theirs, and they had a lot of different variables they needed to factor in. They had a lot of different calibrations that they needed to work on, and they also had some drag on the system from the get-go, before it was even spinning, because of this system. As soon as we took the prony brake off, the turbine spun like much easier. Yeah.
Freely.
So there was definitely some drag on the system that was on there, and they knew that their data wasn't perfect because of this. They did get some data for us. They ended up not having any good data on their rooftop because the wind in Pennsylvania just never cooperates. So
well, and one of the other challenges they had too is they're not there 24/7. These are students that are working on this project. When they would go and work
have
on
an
the
hour or
turbine,
two to work on it.
There was rarely wind,
Yeah.
and if there was wind, it wasn't good. So there's a lot of
And in the beginning,
variables
they were
like that.
getting good wind, but they didn't have their prony brake dialed in, so they couldn't get any data. They just were like, "Wow, it's spinning like crazy,"
And,
So
and they were on a schedule. So this was they had gotten a grant from the state of Pennsylvania to last 15 months, I think it was.
15 months was their project.
So till it was all said and done, they had done the prony brake and concluded that there is an easier way to use the eddy current brake, but the
Right, they
project
were
is
already
done. The
committed.
time
They already
frame
had
is
the
done.
parts purchased, and you can't just scrap it and
So
start over.
That's why we took that idea
Right.
and thought, okay, well, we have the shop here again. This
It's
comes
an easy
back
win
to,
for us. We've got
we have-
machining capabilities. We had scrap materials from Mark II and Mark III prototypes that we actually repurposed, so it was
Yeah.
perfect.
Yep, we just made our own.
And in the end, we have a very solid way now to test and get data. One of the main things from their research that we talked about in that discussion that we had with Nate Siegel from Bucknell was that our design may not be optimal. We knew this all along. I never ever thought that the thing I came up with, 4 years ago, was going to be the optimal design. It was just simply a starting point.
Now, wait.
I'm sorry, what?
The design of it. Are you talking about like
The scoop
furling
designs.
and unfurling?
No.
Oh, the shape of the scoops.
Right. So the scoop designs, I'm
All right.
sorry. We had talked long ago to Northumbria about doing computational fluid dynamics on our design.
Right.
That was 2 years ago. We had discussions with them for the very purpose of helping to get a better optimal scoop design.
Right.
And now Lawrence Livermore is also jumping on that same bandwagon with wanting to do a project or 2 projects with us, specifically looking at our scoop design and our scoop geometry. So all that to say, the harmony you've seen in videos and over the past 2 years is probably not going to be the harmony that will end up being in production. I would say most definitely now,
Right.
because of data that we're already gathering on our wind tunnel, some data and feedback from Bucknell. There's a lot of improvement with our scoop design, which is a good thing. When you're starting somewhere for development, you have to start somewhere. So we've got a lot of room to grow with our scoop geometry.
Right.
And that's pretty cool.
Fear not, the furling remains
Yes,
part
of
of the
course.
design. That is not changing. So
Yes, you will be able to furl it. So things we're looking for, we'll explain when we show footage of our wind tunnel. But some of the things that we're actually looking for are key components to what's going to make Harmony different from other wind turbines out there. And I guess we can go ahead and show that footage.
yep, let's take a look.
All right, so Nate, what is this contraption you've got here?
So here we are at our wind tunnel. It's a makeshift one. We designed it with all stuff that we have in house. But what's really interesting is we can look at different wind speeds simulated by the fan, and we can measure how much amperage we're getting. So this
Milliamps.
turbine, milliamps,
Yeah.
is attached to a DC motor, and then we're able to read the milliamps. So we get a small load. There's 2 bearings in there that shows it spinning, and we have the gold standard right now. So
The cool thing is it's actually putting a small load on the unit, and we're measuring those, the output here from when he turns the fan on. So we're getting to see our low wind speed startup, and then also the performance under a small little load.
Yep. So at low speeds, you can see it does spin.
The little noise you're hearing is our little bearing in that thing is pretty bad.
Yeah. That's the
It's noisy. That's our wind speed monitor.
So, at these low speeds, we're getting like 0.5, 0.6, or milliamps, or 6.5, sorry.
So without a load, this would actually be spinning faster. Like if I take that off, you can see it speed up. So we are putting a load on it, and we're measuring that load on our little meter, which is perfect because it in many ways represents real world conditions in miniature.
Yep. Yeah, it's a miniature generator.
Yeah.
And you can see we have about 3 different wind speeds. So we got a medium wind speed,
Low, medium, and high wind
Yep.
speed.
and we got a high one. So we're looking at comparisons. You can see this is our normal one. We're getting about what is that?
14.5.
milliamps.
Yep.
If we talked about some different geometry changes. One of them that we talked about is right here, just a minor change.
Where
So-
we're doing one large scoop in this case and a little tiny bit of a helix twist to it and a much higher aspect ratio height to width.
So if we put that on there, we're getting
25, 26.
26.
Yep.
So that's almost twice as good.
Yep.
Significant
Significant improvement there. And then turn it off once and then
Yep.
we'll see how that we'll just show these two. We have lots of them, but when it's at a stop, and we'll even put it in a weird spot, like to see if they can start in low wind speed, because that's one of the important criteria.
So we're on low setting, and
there we
it
go.
goes.
So that's one of the things we need to look for in these designs, that they can actually start up in low wind speed, that they're self-starting. So here we're in low wind speed conditions, and if we toggle the unit to where it's, like you can see it's struggling to start in low wind speeds in certain positions, like right there. It doesn't want to start. It does eventually start, but those are considerations we would certainly take into account, where if we have a turbine that's got, it has problems starting in low wind speed, we may rank it lower on our scale. This is good for doing A to B comparative testing, not necessarily giving us any type of coefficient of power or performance rating or efficiency rating of any kind.
And like the type of A to B that we're looking at is we're looking at the number of scoops. We're looking at, so like you see this one has 4 scoops. The one in there has 1. This one has, 2 scoops. We're looking at adding plates. That one
different geometries on the scoops. So we have, I don't know, what, 20, 25 different models that we've been printing, and we even bought like 11 more spools of filament, because this is allowing us to do a very, very large amount of testing of various geometries with minimal amount of expenditure of cost and time. So the 3D printing in the small wind tunnel is great for doing that.
Yeah, it's, I think, definitely directing us to where we want to focus our development in.
So the scoop geometry has a lot to do with how it starts up in low wind speed, the ability for it to produce at maximum RPMs and the high-end performance, and then also just being able to furl that design and close it in is important to us. So we're trying to keep those 3 things balanced. Self-starting, good performance in good wind, and then the ability for it to close and furl in the high wind situation, so we don't overspeed.
Right.
This is what we're going for, guys, and that synergy of those 3 things is really what's going to end up determining what Harmony's very first production run is going to look like.
Right.
And even then, even after we go into production, we may end up further tweaking a little bit more, because once we start getting a lot more data, we might find that we can improve it still further.
Right.
That's the beauty of R&D.
So the last video we did, we were starting to prepare the mold for our next stator, to pour the resin for the next stator.
Yep. So we were actually doing work on our Mark IV generator design. We kind of put that on hold because when you look at what's important in Harmony and in our company and to our investors and to our followers, the most important thing is getting data. We need data. To that end, guys, we spoke in our last video about purchasing a third-party generator. We did receive that. It's here. Yep. We actually have it set up over there where we're doing some testing. The eddy current brake was drop dead simple and got us the data we need without worrying about an extra load or other crap that we have to take in the vehicle with us when we do our testing. So we kind of put both the third-party generator and our generator on hold, shifted priorities, and jumped into doing the eddy current brake. So we have a little bit of other stuff that we did with our generator over the last 3 weeks, but not a lot, because we've been focusing on finishing the eddy current brake.
Yep.
So I think you have a little bit of footage that you want to show about that. was a lot of days waiting for that finally to come out of the oven.
Yeah.
So that's where we are. The generator is kind of on hold right now because we're focusing on something that's more important to the company, and that is getting data. Once we have data, we've got a lot more things that we can do.
Yes.
And a lot more directions that we can go in to finally hone in on the final design and putting this all together. So that data is going to be juicy stuff. And we were outside today. It's windy.
It's the fastest clip I've ever recorded of them talking. It was so cold outside.
Yeah, it was really quite cold. So we're going to need like really big parkas and gloves and everything when we go out and do our road testing here in the winter for sure. Yeah. But I think we're actually going to be doing some winter road testing as soon as we find a suitable place to drive back and forth that we can turn around at each end and
not going to hit wires.
Yeah. Give us a good mile or two of open road that we can test on and then turn around and do it again on the way back and start getting some data. It's not a perfect way to get data, but it is a way to get some data.
Until we can get the turbine
up on the
our
roof
building.
in actual wind conditions, natural wind conditions. The other cool thing is with our truck, we could take it up to Chickies Rock or somewhere around our area that has really good wind, park it, turn sideways to the wind, and let it actually get natural wind turned sideways, where we're not coming up over and squeezing that airflow up over the windshield of the truck. Right. So you don't want to be skewing your data when you're getting data gathering results. And obviously driving behind a vehicle, a truck or a car or anything is going to skew your data somewhat, maybe even a lot, depending on how fast you're going. So making it mobile is nice. We can get some data on the road. We can do a lot of comparing this design to that design. But when we stop and we park somewhere, we can actually get good data at a stationary location, and that would be nice. Yeah. Our eddy current brake is going to allow us to do that remotely and mobily, which will be huge. Yeah. Even prior to getting our generator done or testing with a third-party generator here. It's kind of like a pre-step or a precursor to that testing.
Just a reminder that we have our apparel shop. We are going to be adding mugs to our array. They're not here yet, but I will have a button on our website where you can pre-order them, and they should be here in about a week and a half, I think. We have sweatshirts, hoodies. I was so cold outside. I was like all doubled up, but here's
a double Harmony.
My long sleeve. I can't even do it. My long sleeve Harmony shirt. So, maybe these are great little Christmas presents or stocking stuffers for people Sure. Just an idea. So anyway, feel free to take a look and take a look at the mugs too while you're there.
All right, guys. So that about sums it up for our Thanksgiving update.
Yep.
Next time we talk to you, it'll be Christmas time or
oh my goodness,
in between Christmas and New Year's, something like that.
That's our goal.
Yeah.
We'll see.
Good grief. I have no shopping done. It's terrible.
Oh, well.
Yeah.
There are more important things.
There are. Like Harmony.
Family.
Oh, wait, what? We can... Anyway.
All right.
Thank you for everything. Thank you for following us, for supporting us, for being here as we go through the process of figuring this all out and sharing the journey with you.
Yeah.
It's not a quick journey. It's not a simple journey. But we are getting there step by step by step. And that's what's important, making that progress and getting to the end goal of finally being able to be in production with units that you're going to be happy with.
Yeah.
So.
And there are several of you who are donating regularly through Patreon and PayPal. So we thank you for believing in us and for being an active supporter in our journey. We wouldn't be here without you guys. We wouldn't be here without people who invested in us over the past couple of years. And
we have been getting some questions over the past couple of months more heavily where people are seeing us, finding us and saying, wow, how can I invest? I'm sorry, but we do not have investments open at this time. And we do not have any plans to take further investments even in the future. Right. I'm not saying it's 100% out because of course nothing is certain. It's the future. But our goal is that we do not need to do, that we don't want to do another raise anytime in the future. So we're trying to do our best with consolidating and holding on to the money that we have, using it very wisely to then help us move forward with our work here and even blending in the work that we're doing on the side, peppering that in to try and help offset our costs on a monthly basis.
Yep.
So we're doing everything we can to be smart, to be intelligent about how efficient we are with our money and our funds so that we don't have to do another raise. So if you want to support us, unfortunately, we do not have investments open at this time and have no plans on doing them in the future. Donation would really be the only thing that you could do at this time if you feel strongly and want to help in some way to support Harmony.
Right.
Or, buying some apparel.
there's
of course.
there's the little shop too. So.
But yeah, donations or buying apparel are probably about the only two ways you could help financially support us at this point.
Right. Okay.
Okay. Until next time,
All right.
guys.
Thank you, guys.
Happy holidays from Harmony Turbines and the team here. Harmony Turbines. We now have the power to change the world.
So what are we testing here?
Eddy current to make a brake for our dyno.
Yeah, dude, that's definitely pulling my hand.